Earlier, we saw that if we wanted to calculate the area under a curve, we could take the limit of a Riemann sum as n goes to infinity. Remember that the Riemann sum is a sum where we're adding up the areas of these different rectangles. And each of those rectangles is length times width, or height times base. And the heights are all function values, and the bases are all delta x. And we've got this sum inside, and it's kind of interesting because we don't know how many terms that we're adding together, right? I mean, we're adding together n terms, but n could be anything. It could be 10 different terms, it could be 100 terms, it could be 378 terms, it could be 56,921 terms, and we can't write out all of those individual terms, so we kind of have to do this ... thing in the middle to be like, hey, we're adding more terms, but we can't write all of them out, so we're just going to skip over all of those. And there's actually a really nice notation that we have called sigma notation that allows us to write a sum like this in a more formal way. So I want to give you that notation. I want to show you what that looks like. So here on the left-hand side of this new equation, we have that exact sum inside. And if you look at this, we're adding together a bunch of terms, and all of the terms are exactly the same, but there's one little thing that's changing, right? Each of them is f of x sub something times delta x. And it's just the subscript that changes. It goes from 1 to 2 to 3 to 4 to 5 to 6, all the way up to some number n. And there's a way that we can write these sums called sigma notation. It's called sigma because this is a capital sigma, a Greek letter. And this basically says we're taking a sum and all of the terms are in the same form, f of x sub something dx, and that something, that I, changes. It ranges all the way from 1 and it goes all the way up to n, changing as integer values. So it's all the integer values from 1 to 10. So the first term is f of x sub 1 delta x, as you can see here. The second term then is f of x sub 2 delta x, which is what we see here, etc. Then we've got 3, and it goes all the way up to x sub n. So this is just a shorthand version of writing out all of this, saying we're taking a sum, all of the terms are very similar, but there's one little thing that's changing each time, and that little thing, the subscript in this case, starts at 1 and keeps increasing all the way to n. It's just a slightly less involved way of writing out a sum like this without having to write out a bunch of terms. Now, knowing this, let's write out what the area under a curve is, the limit definition of the area under a curve, but using sigma notation. Now, we've got a equals, and we know it's the limit as n approaches infinity of the Riemann sum, and we know the Riemann sum is a sum of all of these values, and we just saw that we can express that in sigma notation. So this is the limit as n approaches infinity of the sum as I ranges from 1 to n of f of x sub I delta x. That's using right-handed rectangles, or the right endpoints of each of those little intervals. But we also said that we could define it with the left-handed rectangles, or the left endpoints of each of those intervals. So we could also say it's equal to the limit as n approaches infinity of the sum as I ranges from 1 to n of f of x sub I minus 1 delta x. If we decrease 1 from the subscript there, that moves over to the left one, and we're looking at the left side of each of those little subintervals instead of the right ones. But we also said more generally that the area was equal to the limit using any sample points. We didn't have to choose the right endpoints or the left endpoints. We could choose any sample point in each interval. And we can write that as f of x sub I star delta x. And so these are actually three different ways using sigma notation that we can define the area underneath a curve using Riemann sums. Three different ways of doing that. And each of these takes a lot less writing than the definitions we already saw, where we had to write out a bunch of those terms individually and do the dot, dot, dot. Now, using these definitions, I want to do one problem together where we're going to be given a specific function and a specific interval, and I want us to write out an expression for the area underneath that curve using limits and sigma notation. So we're going to do an actual example with an actual function. So let me give you that. Let's let A be the area of the region that lies under the graph of f of x equals e to the negative x between x equals 0 and x equals 2 using right endpoints find an expression for A as a limit and we are not going to evaluate that limit. That's going to be a complicated limit to evaluate. We do not have the tools to do that now, but I just want us to write this as a limit. I want us to go through one example with sigma notation where we're actually writing out an expression that could be calculated for the area underneath that curve. All right. So in this problem, since A is equal to 0 and B is equal to 2, those are our two endpoints, we know that if we want to figure out the width of these intervals, the width of these rectangles, delta x, that's going to be 2 minus 0 over n, which is simply equal to 2 over n. And then earlier we saw that x sub I was equal to a plus I times delta x, basically the starting point plus however many intervals you're moving over times the width of one of those subintervals. And in this case, we know that a is 0, and we said that delta x was 2 over n, and 0 plus I times 2 over n is 2I over n. So we have expressions for delta x, and we have expressions for x sub I that we can plug into this formula. So let's write all of that out. The area is equal to the limit as n approaches infinity of the sum as I ranges from 1 to n of our function evaluated at x sub I. Well, the function, if you'll recall, is e to the negative x. So that's going to be e to the negative x sub I, which is 2I over n, times delta x. And in this case, delta x is 2 over n. So times 2 over n. And I'll put that in parentheses just to make it a little bit nicer. And this is an expression for the area underneath that curve expressed as a limit of a sum. So we do not have the tools to evaluate this limit yet, but this is one step closer to formalizing how we can do these calculations to figure out these areas. So if you're taking a calculus class with me right now and not watching these videos elsewhere on the internet, for this particular section, I'm not going to ask you to evaluate any of these limits. The point right now is for us to get practice in a very rigorous way writing out these limits of sums so that we can actually get a mathematical expression to evaluate the areas underneath these curves. We might use a computer to evaluate this. We might evaluate some of these by hand using some formulas later on, but to even get to the point where a computer could give us the area under a curve, we need to have an expression for it to evaluate. And so that is what we're doing right now. We have come up with this expression. So moving forward, we either need to find a way to evaluate it ourselves or have a computer do it. But we've done the legwork of figuring out what the right expression is.